And thanks to anybody who's here out of the goodness of their own heart or to learn something about astronomy, which does my heart good. It also does my heart good to introduce the first speaker at this year's Perimeter Astronomy Conference. Better about the name. Those who know me know the joke behind that. She is my soon-to-be academic sister. See, when you get PhDs, whoever your advisor is your academic father. She's getting one from my academic father, so that makes her my soon-to-be sister sometime in the near future.
Yeah.
So apparently very, very soon. Yeah, Mike is really pushing that that
Why do you guys
frame.
talk about me?
Me? What?
Yeah.
Are we? Okay, good. So, clearly in astronomy, we wind up with the same sense of humor, what they teach us. So she will be teaching us all about AGN from emission and absorption, apparently, of stellar features. I'll let you take it away. Just turn on. That. You should be There we go. All right. I give you proto-doctor Crystal Milka. And that's as low as I can get him without turning him off entirely. I think it's in that. I can trust you guys to not fall asleep. You sure? No. Who needs another donut to stay awake? Okay. I'll let her take it over.
All right. Everything was good in terms of proportions. So, hi everyone. Thank you for coming for whatever reasons you did come for, whether it's extra credit or hear about awesome astronomy. So, just to get a quick idea, how many of you are in introductory astronomy? Okay. How many of you have studied astronomy past that? Past introductory? Okay. And how many know what an AGN is? All right. Trouble. All right. Well, I'm going to go into we call them active galactic nuclei because they're at the center of galaxies. And when we observe them, what we see is that right here in the center of this nice little example galaxy, NGC 1068, your entire host galaxy. So imagine that. All of the light from millions and millions of stars that exist in the whole galaxy, this one thing at the center is brighter than that. But they also emit radiation over a broad range of wavelengths. So we get radio emission from them. We see them in the visible, so what we see here coming from the sun. But we also see them in the more energetic wavelengths, like UV or gamma. And if we zoom in, what we also see is that they have this rapid variability. So sometimes these objects change how much they're emitting over the course of a few days, and sometimes they change over the course of a few hours. And if you guys have learned anything from astronomy, it should be that astronomy is very, very big, and the timescales are very, very long. So whenever we talk about anything in astronomy, we normally say that, oh, this takes like thousands of years, or this takes millions of years, or the universe is this many billion years old. Well, these things can change within a matter of hours. I'll let that a little more later. But it just means that the velocities that we're seeing have this huge range. So, what kind of object could be creating something that has such a high velocity, or such a high luminosity, brighter than the entire galaxy sometimes, and is also able to change on such small timescales? Well, we think that it's a black hole. It's a very, very, very big black hole. So most of the time when people talk about black holes, they're talking about a single star dying and turning into a black hole. These things are anywhere from like 1,000,000 times the mass of the sun to 1,000,000,000 times the mass of the sun. So they're pretty big, they're pretty heavy. But, as many of you might know, black holes are black. They don't emit light, right? So if we're seeing these things and we're seeing them giving off a bunch of light, how are we doing that? Well, there's a black hole, and then around it, there's a thing that we call an accretion disk. So this is actually the source of the light. A lot of the way that we describe sizes in astronomy is based in light days or light years. So that's just how far light can travel in a day, or in this case, 10 days. And this is actually fairly small. So this is a really bright, hot source of the light. This is where everything is falling towards the black hole. Because remember, black holes don't suck. Things fall on them. Because it's just gravity. It's just gravity doing what it normally does, just it being really giant and in the center of the galaxy. So things fall to the center. They fall towards the black hole. They burn up. They break apart. They fall onto this disk. How many people have seen Interstellar? Okay, it's like at least half of them. You were there.
I was.
Yeah, we watched it together. Do you guys remember Gargantuan? And it has like the accretion disk, had those bright rings of stuff falling on the black hole. Well, that's it, except more real and less cool. All right, so this is where the light actually comes from. And then around the accretion disk, we have this thing called the torus. It's shaped like a donut or like a bagel or whatever breakfast good. It's shaped like that. And these can vary in size and height. And sometimes they're really, really thick. And they're almost like one big solid object. But they're just made of gas and dust. So sometimes they can be really clumpy. And you can get light peeking through. And then we have this thing, when we talk about AGN, we talk about these broad line regions, or the narrow line regions. And this is what I'm going to be talking about today. So there are these clumps of gas above and below the AGN. And these clumps of gas reflect light. So light comes from the accretion disk, gets scattered, and depending on where these clumps of gas are, the light will have certain velocities. The gas will have certain velocities. And so when I talk about narrow lines and broad lines, what I'm actually talking about are these emission lines, okay? This is like the only serious plot that's going to talk. So these are two different AGNs. This is NGC 1068, which I was showing before, and this one's NGC 4151. These are two different types of AGN. Notice that this one down here on the bottom is fairly flat, has a fairly flat continuum, and then has these skinny little lines. So NGC 1068 has narrow lines. And NGC 4151 has, well, it also has some of these narrow lines. But then it also has maybe some broader lines as well. And so when I talk about narrow lines, and when I talk about broad lines, what I'm actually talking about is literally just the width of them on the plot. So nothing fancy. Do you guys know what Doppler broadening is? Do you know what Doppler shift is? I know what the 10-10, 10-20 curriculum is. So I know what you guys are supposed to know. All right, so this is basically just, you've got stuff, it's in a disk, and it's rotating. Some of it's going red and some of it's going blue. And when that happens, you get some emission at a certain wavelength, and then you've got some of it being blue shifted and some of it being red shifted. So instead of seeing a nice skinny line like these, the line ends up being broadened to account for all the stuff that's being red shifted on one side and all the stuff that's being blue shifted on the other side. And the more that it's being broadened, the wider this line will be because it's broadened, wide. We're really bad at naming things, but sometimes they're really straightforward, like this. So during my talk today, I'm going to be talking about the narrow line region. So this is the region that is completely above the torus, and it doesn't have the highest velocities that you might see in an AGN. That would be the broad line region because it's closer to the source of emission. But we like it because this is complicated. This top one is complicated. There's a lot going on. But this one down here is kind of simple and kind of nice. Nice and clean. All right. So some of the other AGN components, I'm just going to gloss over because I don't really care about them. They're cool, sort of. You can have a radio jet. Specifically, most AGN do have some kind of jet that is visible or measurable in some kind of context. But you really need to be oriented properly to the AGN in order to see it. So yes, AGN have jets. Are they cool? Yes. Do we really care about them? No. We're just going to move on. So, talking about AGN, these active galactic nuclei, there are a bunch of different types. You could have Seyfarts, you could have dwarf Seyfarts, you could have Seyfert 1, Seyfert 2, you could have narrow line Seyfert 1s, you could have VLX, you could have blazars, you could have optically violent variables. Lots of weird names. But the best way to break this down is just by orientation. So depending on the type of AGN that we're looking at, we may be seeing a jet, which means that it's radio loud. Or we may not be seeing a jet, which means that it's radio quiet. We could be looking directly into the torus, which means that we can't really see the accretion disk, and we can't really see the broadline region. So that would be edge on, and those are our Seyfert 2s. So in these, we're only seeing the narrow line region. Or we could be seeing the narrow line region and the broad line region, and those would be our Seyfert 1s. And those are more face on. So anytime anyone talks about these different types, this is basically what they mean. It's just a breakdown of how the galaxy is oriented with regards to us. And this isn't really something that we see change. Because again, talking about astronomy, these things take millions and millions of years. So what I'm going to be talking about is I'm going to be talking about the narrow line region within Seyfert 2s. So these more edge-on AGN. And why do we care? Well, we care because science. Science wants us to care. So AGN are really important. They are very large in terms of scale, but they're very niche in terms of just topic. So you may think, oh, well, I'm looking at a galaxy that doesn't have an AGN. Why do I care? Well, black holes, these supermassive black holes, exist in almost all galaxies, including our own. But they're not always lit up. So sometimes they're active and sometimes they're not. And even if they're not active, they still help form the galaxy that they're in. So anytime you want to try and figure out how galaxies are forming, go on even smaller scales. There's an interstellar medium, and stuff is being thrown into the interstellar medium. And then that stuff gets turned into solar systems. So if you want to talk about planet formation, you need to know what's going on with an AGN. And there are some other things that go into this. The main thing, though, is what we call feeding and feedback. So basically, stuff falls on the AGN, and stuff kind of gets spit back out. Now, it doesn't get spit back out of the black hole, because once you're in the black hole, you never come back out. That's just how that works. So there are some things that fall towards the black hole and then maybe get shot out before they actually fall in. They get diverted by magnetic fields. Those we call outflows. But then you also have the accretion disk of the AGN. It's very bright. And so as it's sending out radiation, it's going to be pushing on clouds of gas. And those are outflows too. So there are a bunch of different types of inflows that you can have and a bunch of different types of outflows. And those have the strongest and largest impact on their environment. And that's what I studied. That's our group studies. Yeah. And then more interactions. Yeah. Okay. Difference between photometry and spectroscopy. Photometry, you count photons, so you just go out and see how bright something is. Spectroscopy, you care about where those photons are coming from. So you're actually looking at the individual wavelengths. It's like, every time I reference Pink Floyd, every time I reference it, less and less people know what I'm talking about. So you take a prism, you find some kind of like new age store, and you find like some crystals hanging out, and you shine some light through them, and it turns into a rainbow. That's what we do, but with science. So what I do specifically is I combine these two things, or other people have combined them, and I take advantage of it. So if you were to go ahead and look at a picture online, say a picture that you wanted to put into a presentation, you would try to find a picture that has maybe the most amount of pixels, because you want it to have a better resolution. What my research is I have images of AGN where every single pixel in the image is a spectrum, where it goes like this and it spreads out the light. So I'm doing both. I get photometry, I get to know how bright something is, and I get to look at different parts of the picture and say, oh, hey, there's some bright stuff up here. Oh, and some dark stuff down here. What's up with that? But also, I get to look at the spectra. And so I know, oh, hey, there's some red-shifted stuff up here. And oh, hey, there's some blue-shifted stuff down here. That's really cool. What does that tell me? So this is called integral field spectroscopy. Sounds really cool. My favorite thing. All right. So using this is a telescope. It's down in Hawaii, I believe, top of the mountain. Also has a nice little laser to do science with. You guys don't really care about this stuff. We do science with this thing. And when we do that, we see some cool stuff. So this is not the AGN that I work with, but I have worked on it before. Did I make this call? No, I didn't make this call. Fisher made this call. Stole it from me. He stole it from me.
Are you sure?
And so with this, what we see, we're looking at an AGN. We see sort of a disc-looking thing, where on this side it's blue-shifted, and on this side it's red-shifted. This is just evidence of rotation. But then we also see this other thing, where there's all this stuff that's blue-shifted. When something's blue-shifted, that means it's coming towards us. And when it's red-shifted, it's going away. And then we see some blue-shifted stuff and then some red-shifted stuff here. It's not very red-shifted, but it's red-shifted in comparison to the rest of this. And so we see this filament and we say, what is that? Why is that there? Like, we see all this rotation, and that looks great, and that looks fine. That's what we expect. But what is that? Well, if we look at it in other imaging, what we see is that it's actually inflows. This is a stream of material coming up from some far-off dwarf galaxy. It's basically being pulled in by Markarian 509. This is this AGN, being pulled in towards us, and then it turns around and heads down towards the AGN. So that's one of the things that we've been able to see. Another one is Markarian 573, which is very cool. We've gotten some really good observations with this. Again, Fisher. He's all right. He's fine. It's kind of hard to see in this image what's going on. The dark spots are where we see dust, or where we don't see it because it's dark. And the light spot is where we're seeing emissions from gas being lit up by the AGN and other things, but mostly the AGN. And so we can trace out, if we look at specific emission lines, we can trace out, hey, this is where all the hot stuff is. And then we can trace some of the molecular gas, which is cooler. It's still kind of hot, but it's definitely cooler. This is the stuff that's going to form dust. And this is the stuff that's going to fall onto the AGN and actually feed it. Hence, influence feeding. But we can actually trace that stuff out. And when we do, it actually lines up perfectly with the dust, which is really cool. And so if we look at some velocity maps, I haven't actually said that that's what these are. These are velocity maps. So we're tracking velocities of different gas within the field of view. We can see, hey, there are these outflows, really, really strong outflows. We see stuff that looks like rotation. This right here, the CO 2.3 microns, that's actually an absorption line. Those are stellar features. So not only are we looking at really, really hot gas, but we're also looking at stars, and we're tracking them. And when we do that, we can see the rotating disk, and then we can see some of the cool gas, and then we can see some of the hot gas. Now, this isn't a jet, but it's basically a jet. It's like two sides of stuff streaming out of the AGN. So think of a jet, but like smaller. That's what these outflows are. And we get to see all of that with these integral field spectroscopy, or IFUs, which is an easier way to say it. So what I do is I spend my whole life looking at one AGN. Don't get aggressive. Seriously, don't do it. It's fun. Anyway, so I'm looking at this one AGN called Markarian 3. And this is actually a reverse image. Not to confuse you, but to confuse you. This is a reverse image. So the dark stuff is actually the emission, and the white stuff is the dust. Yeah?
So it's like a negative.
Yeah, it's a negative. Yeah. And if we were to actually see this in like a nice little diagram form, that's what it would look like. So this region right here, this, maybe I'm lying, I don't know. I look at them so many times where it's like a negative and then it's not a negative that now I'm confused myself. Anyway, so this is the narrow line region. That's that region that we talked about. It's outside of the AGN, but still part of the whole system. And this is where we expect to see those inflows coming in and those outflows being sent outwards. So we look at this closer. This is oxygen 3. So this is doubly ionized oxygen. And these brackets here, this is just random terminology. The brackets mean that it's forbidden. So it's hard to produce. You need to have the very perfect conditions in order to produce it. But it's very hot emissions. So this is what we expect some of the outflows to look like. Okay? So this is what it looks like with Hubble. You want to know what does this look like if we take those IFU observations. Will we see the disk that kind of looks like this? Remember before we could see the disks of rotation with the other AGN. Are we going to see the same thing with this one? Who knows? Let's look. Well, what we actually see is that even though the majority of the emission coming from the narrow line region actually looks like this little, kind of looks like a snake, kind of looks like a backwards S, but also it looks like a rabbit. Here are the ears. Here's the thing. Here's the back foot. And here's a random chicken foot. So a rabbit went and stole a chicken foot, and it's running away. Right? This is all I've looked at for 5 years. So anyway, so even though the majority of the emission from this AGN is actually in this shape that you see here, we do see individual components. So we go ahead and we look at that single narrow line, and we see that it's actually made up of, say, 3, 4, or 5 different components, all kind of stacked on each other. Because remember, when we're doing astronomy, when you look out into space, it's not just like a flat image that you're looking at. You're seeing multiple levels. You're seeing different distances of things. So sometimes they end up getting all smushed together, smacked on top of each other, and that's what you see. But using math and computer programs, we can sort them out. And when we do that, what we see is what I am proposing is rotation. So similar to the fossil that you saw earlier, I'm saying that this is rotating gas. There's a disk here that looks like this, red shifted on this side and blue shifted on this side. But does that make sense? Does that make sense if we look at, say, the whole galaxy? Well, if we look with stars, I like that there's a suit here. That's not part of my presentation. All right, so if we look with stars, what we see is there is a disk right here, pointing in this direction, where it's blue shifted on this side and red shifted on this side. But wait a minute. That doesn't match. Why doesn't that match? This is a disk of gas, where it's red shifted on this side and blue shifted on this side. And this is a disk of stars, where it's blue shifted on this side and red shifted on this side. Now this can happen. It is a thing that can happen. The stars and the gas, they don't have to actually be aligned. But it's cool. It's cool when it does happen. It means that stuff is getting moved around. Maybe something came in and knocked everything out of place. So it's noteworthy. But this is what it looks like on the small scale. Remember that this is the narrow line region, which is part of the AGN, which is at the very, very center of the galaxy. So this is the small scale. How does it compare to the large scale? What we did, and I think some of the people here have also worked with data from the Pecky Point Observatory, is we got spectra from this observatory. Georgia State gives them a lot of money, like a lot of money. So we just get time. And so what we did is we pretended that we were getting ISU observations. Now remember, those are, you have a spectrum at every single pixel. Well, we don't have one of those instruments. So we can just take a spectra depth and just do a bunch of different angles. And you sort of get the same thing. And when you do that, you get something like this. Now, this is plus or minus 1.5 arcseconds. And that's just width on the sky. This is plus or minus 15. So this is 3 arcseconds wide and this is 30 arcseconds wide. So 2 very different scales. And these are stars. So when we track the stars on the large scale, we do see along this major axis of the disk, there's blue shifting in this corner and red shifting in this corner, similar to the small scale. So yay, things match, that's good. But what happens if we look at the gas? It doesn't match. Nothing matches. Just nothing means anything anymore because none of it matches. So when we look at the large scale for the gas, what we see is that there's a whole nother disk. And it's like 90 degrees from the small scale one. And so what does that mean? How is that possible? How are we seeing all this disrupted gas just doing crazy things, not just at the large scale, but also at the small scale. It can't just be from the AGN. So trying to figure out why that is, we found that this is my little guy right here. James Markarian's ring is very small and cute. And this is a companion over here. It's a nearby galaxy, spiral galaxy. It's bigger than my little guy, but they don't seem to be like they're very good friends until you look at them at certain wavelengths. And then you see, oh look, there's all this gas coming from this companion over here and streaming into Markarian 3. It's just like T-boning Markarian 3, hitting it from the side, tons of gas is going through, coming out the other side and twisting around. There's a lot of gas moving around. And so we want to know, is this a thing that could be affecting the narrow line region, even though it's on such a small scale in comparison to this? Because this little circle right here is like 60 by 60 arc seconds. And keep in mind that I think the narrow line region might even be smaller than the red dot. So we're talking about really, really different scales. And so is this something that we could even see in the narrow line region? And the answer is yes. Yes, we can. Mildly preliminary. So what we see is that if we look at the cooler gas in the narrow line region, which is harder to do, we do see streams of material coming in from this northwest side. And then just moving into the AGN, gathering onto the narrow line region. So, in conclusion, there's a lot of stuff going on. This is one single AGN, and there's a lot of stuff going on. So, my little diagram, because it makes things make sense. You have the small scale and you have the large scale, and then you have gas and you have stars. Good news, stars are doing what stars are supposed to do. That's a good thing. Bad news, gas is not doing what the gas is supposed to be doing. But that's also good news, because it means that interesting things are happening. There's a stream of gas coming from a companion galaxy, sort of sidelining my AGN and just disrupting everything, creating like misaligned disks both on the small scale and on the large scale. And this is something that's really cool for us because in the long run, if we figure out things like this, then we can figure out how these galaxies are forming and how they're evolving and how do we get to where we are now and here in our galaxy. So, any questions?
Give her a round of applause. Time for like one, maybe two questions.
All questions are good questions.
Yes, we get it. You're 10, 10, and 10, 20 students, and even physics students, and not your expertise.
How do you
where are these pictures coming from? The Hubble?
Yeah, so some of them are from Hubble. This one
There are a
from
couple of seats in here for those who are standing.
this one from the Palomar 48-inch telescope. 48 inches. But then this one is from a different telescope. It's at a completely different wavelength range. It depends on what we're talking about. So these things are from the visible wavelength ranges, and they're from the Apache Point Observatory 3.5 meter in New Mexico. We're actually going out there in November, just for fun.
One of the nice perks of being an astronomer, you go places.
For fun. Weird.
Well, no, you go to work.
They have sand dunes, and you can ride a sled down the sand. What? Yeah. Last time I went, I had pneumonia, so this time it's going to be better. This is seen in the infrared. Yeah. And like I said, it's done with that IFU integral field spectrometer, where you have like a whole image worth of individual, what's the word? Refractors. Triangle.
Prism?
Prisms. Thank you. Yes. So it depends on what you're talking about. They all do different things at different wavelength ranges. Any other questions? Do you guys like the bright colors? I like the bright colors.
All right, let's give her one more round of applause. We'll have our next speaker, a repeat speaker from last